Now what I'm going to do, I am going to modify this RTL. Okay, I'm going to do on the fly here. So CP counter underscore opt to counter underscore opt 2 dot v, gvim counter underscore opt 2 dot v. Now what I'm going to do, instead of saying q equal to this, I am going to write the other statement, what we discussed in our case 2. Count of 2 colon 0 equal to 3 tick B100. Let's see what happens. This is what I'm writing here. Okay. So now I'm using all the 3 bits of the counter. That means I expect all the 3 flops to be present. Correct? All the 3 bits to be retained. It's not retaining only 1 bit. All the 3 bits of the counter are retained. Let's see what happens. So let us launch Yosis here. So read liberty-lib mylib lib sky 130 read verilog counter underscore opt 2 dot v. Okay, then synth hyphen top counter underscore opt 2. Okay, I think the file name is counter underscore opt 2, but still the module is counter underscore opt. So we are expecting 3 flops to be inferred here, correct? Let's see what happens here. Bingo, you go here. 3 flops are inferred. This is exactly what we expected. Okay, now let us do dff lib map mylib lib. Oops, I think I missed the liberty option here. Minus liberty. After this, we have to do our ABC. ABC hyphen liberty lib slash mylib. Sorry, mylib lib sky 130. So I'm going to show it again here. See, this is clearly something other than what we thought. We are seeing so many. See, first let us look at how many flops we are seeing. This is something interesting. See, I'm seeing 1 flop. I'm seeing 2 flop. I'm seeing 3 flop. Earlier we saw only 1 flop, correct? I'm seeing all the 3 flop. So I'm seeing count. This is my count of 0. This is my count of 2. This is my count of 1, correct? This is my 1. This is 2. All the 3 bits of the counter are in place. So I think this is the logic for, let's see where the Q is coming from. So the Q is coming from this. You see, the Q is coming from this. I think this basically you need to add an incrementer. You need to have a incrementing circuit, right? Basically you need to have an adder. So I think these are the logic which is making the adder. But let us look into this. Let us concentrate on this. This is what is generating my Q. The Q is coming from here, where this is the bit 2. This is my bit 1 and this is my bit 2, bit 0, correct? See, kindly look at this. This is coming from the A input of this NOR gate is coming from bit 1. B input is coming from bit 0. C input is coming from bit 2. And C input is an inverter. There's a C underscore N is there. That means C input is a negated input. So let's see what it has done. It is looking for 3 tick B100, correct? That means we are looking for expression of Q as something like this. We are looking for the expression of Q as Q equal to count 2 dot count 0, sorry, count 1 bar dot count 0 bar. Correct. This is the expression we are looking for, 100. Correct. Now let us see what expression we got. The expression we got here is, it's a 3 input NOR gate with C inverted and connected to bit 2. So let's look for the expression. Let me write it again. So we are looking for Q equal to count. I am going to write it as C of 2 dot C of 1 bar dot C of 0 bar. Basically I am looking for 100. Correct. This is what my aim is. Let's see what we got. We got a 3 input NOR gate with this inverted. This is my bit 2, this is my bit 0, this is my bit 1. Correct. This is what we got here. Correct. Let us look at this Q logic alone. Q is coming from this NOR. Bit 2 is connected to C underscore N. This is the negated C, A and B are there, which is coming from bit 1 and bit 0. Let's go and evaluate this expression. So what is the expression for this? So the expression for this will be C0. This is my C, correct? The C stands for count, plus C2 bar, the whole bar, correct? Now I'm going to apply the basic De Morgan's theorem. So break the bar and change the sign. So it becomes C0 bar dot C1 bar dot C2 bar bar. So bar of a bar is the same thing. So C0 bar dot C1 bar dot C2. Bingo. This is exactly what we want. This is exactly what we want, and this is exactly what we are getting. So in the previous case, we saw that only this expression was there. In the previous example, Q was becoming C0 bar. Why? Because only count 0 was getting used. The other two was not getting used. Correct. Count was C0, not C0 bar. Sorry. It was C0. Correct. Whereas here, we are seeing that all the 3 bits are getting used, because that's how we wrote the code. And all the 3 flops are also preserved because of this, because we are using their outputs. Whereas in the previous case, only count 0 was used. So count 1 and count 2, the flops pertaining to those 2 bits and the logics pertaining to those flops are also completely knocked off, because there is no need for those logics. So the synthesis tool will start optimizing it completely. That's a very important point. So if you see, there was a logic feeding the flops also, that whole incrementer logic here. See, kindly note this here. Let us go back and see that. That's very interesting to note. Here, the rest of the logic, what you're seeing here, this NOR, NAND, NAND 3, invert, this, all this logic are pertaining to the incrementing logic, because the count is getting incremented by 1 on every clock cycle, correct? So it's something like an adder circuit kind of. But in the previous example, we didn't see any of them. Why we didn't see any of them? The reason was very simple. The outputs are unused. If the outputs are unused, the flop got optimized. If the flop got optimized, though you don't need any logic feeding the flop also. See, ultimately this logic is what is feeding this flop. Now if this flop itself is not needed, you don't need this logic which is feeding this flop also. So all this logic also got optimized. We saw only this logic, bit 0 having an inverter and coming back to bit 0. This is the only thing we saw, which is present even now, because bit 0 keeps toggling every cycle, correct? But the other, all these things were optimized away in the previous example, but it is not getting optimized away here. So this is a very, very important optimization technique. So what all outputs are not going to be having a direct role in determining the primary outputs of the module, all those intermediate outputs will be optimized away. All those logic feeding those intermediate outputs will also be optimized away. That is what we learned here. Okay. Thank you.